Okay, in the last class we have discussed about the architecture of 8254 and controller format of 8254. So today we will discuss about how to interface 8254 to 8086, and then we will discuss some of the modes of 8254. Okay. Interfacing of (8254) to 8086. So this 8254 also will be interfaced to 8086 in a similar manner to that of 8255. So we know that here also in 8254 A1 A0 is going to decide the counters or counter load register. Zero zero means its counter 0, 01 means counter 1, 10 means counter 2, 11 is control register, so if I take this 8086 and 8254, this is 8254, this is 8086, so this A0 A1 of both the devices will be connected together. A0 of 8086, A0 of 8254 will be connected together. A1 to A1. Similarly, we have read bar, write bar. Then we have to generate the chip select of this particular 8254 IC. I will use only this address of these three counters. Inside this there are three counters: counter 0, counter 0, counter 1, counter 2, and control load register. I will use 8-bit addresses of these counters. For that I have to use A7 to A0 of 8086. Out of that A1 A0 I have connected to A1 A0 of 8254. Then I will use A2 to A7. This is A2, A3, A4, A5, A6, A7. If I connect through an AND gate, and if I connect these two chip select bar of this one, now if I connect directly this A7 to A2 to this inputs of the NAND gate, then the address of counter 0, counter 1, counter 2 control register will be FC, FD, FE, FFH, which is similar to the 8255 addressing. Okay. To have a different feeling, I am assuming here some inverters are connected. Now what will be the address of counter 0, counter 1, counter 2 and control register? This is mapping. A7, A6, A5, A4, A3, A2, A1, A0. So these two pin will be connected to A1 A0 of the corresponding microprocessor pins. This is 0 0 means this will select counter 0, 0 1 means counter 1, 1 0 means counter 2, 1 1 means control word register. Now this will be A1 A0. First of all you have to select the chip. After that only based on this A1 A0 we can select counter 0, counter 1, counter 2 or control register. So how to select the chip? For that CS bar should be equal to 0. Okay. For what values of A7 to A2 this output will be 0. If all are zeros then only output is 0. 0 0 0 0 0 0. This should be all zeros whether you want to select counter 0, counter 1, counter 2 or control register. So you have to fix these values to 0 0 0, 0 0 0, 0 0 0, 0 0 0, 0 0 0, 0 0 0. Once these are zeros, output of inverter will be ones. If all the inputs of NAND gate are 1 then only output is 0. If any one of the input is 0, output is 1. Okay. So what will be the address of this counter 0? This 4 bits will be 0, this 4 bits will be 0, this is 0 0 H. So this will be 0 1 H. This will be 0 2 H. This will be 0 3 H. So see about the interfacing of 8255 to 8086. Now we will discuss about the modes of 8254. So this 8254 can operate in 5 modes. So before going for these modes, we know that this 8254 is having 3 counters, 3 16-bit presettable. Down counters. Which operates on negative edge. You can also call as presettable negative edge down counters. So what is meant by presettable? Presettable means, so we can preset the flip flops. Basically in counter we will be having flip flops. So each flip flop can have 2 operations, preset and clear operations. Okay. So in order to preset, there will be 2 signals called preset bar and clear bar for any counter. If this preset bar is 0, clear bar is 1, then implies Q is equal to 1. This is called preset operation. For clear operation, preset bar should be 1 and clear bar should be 0, implies Q is equal to 0. Q is equal to 1 is called preset operation, Q is equal to 0 is called clear operation. For normal operation, we will keep both the clear and preset values as 1. So we can preset these counters and they are down counters. Suppose if I want to count 5, initially how to load 5, then 5 will, after first clock signal, it will goes to 4, then 4 to 3, 3 to 2, 2 to 1, 1 to 0, then 0 to, it will go to 5. This is the timing diagram or state diagram of mod 5 down counter. Then these are 16-bit counters. We have 3 such, which is counter 0, counter 1, counter 2. Negative edge. So this counting will take place at the negative edge of the clock. Negative edge means which is a transition from 0 to 1. Negative edge means transition from 0 to 1. So, if I take mode 0, there are 6 modes of the operation. Mode 0 is interrupt on terminal count. So, we know that this 8254 is having different signals like clock. Suppose if I want to use counter 0, so clock 0 you have to use clock 0. Okay. So, I am taking this square wave. This clock of 8255 can operate between 0 to DC to 10 megahertz. Depends upon the application, we can operate this clock with frequencies ranging from DC to 10 megahertz. This is the clock. Of course, I am plotting this ideal clock. The practical clock will have some slopes at the transitions. This is clock 0 of counter 0. Then we have one right bar signal. 8254 is having right bar signal. Okay. So, this right bar you have to make low in order to initialize the counter. So, after making this, we can load any count value, say n is equal to 4. I am loading n as 4. This n can be any 16-bit number, okay, because these are all 16-bit counters. So, we can feed from 0000h to FFFFH. For the sake of simplicity, I have taken just only n is equal to 4 for explanation purpose. And gate of this one in mode 0 has to be keep always high. Gate 0 has to be made high. Here I am using only counter 0 signals. We can explain the same thing for counter 1 as well as counter 2 also. So, gate signal has to be made high. Then once this right bar goes to high, the next immediate negative edge signal, negative edge transition. So, initially out 0, initially out will be 0 only. Now, here onwards when n is equal to 4 and right bar goes from low to high. So, after becoming high, the next negative edge of the clock, this one, here it will start counting this counter. So, as I have told, this counter is a down counter. So, this n is equal to 4 becomes 3, this is 4 over this clock signal over 4, then 3, 2, 1, and this becomes 3 because 0 to 3 will be modulus 4. So, normally this is mod 6 counter means 0 to 5. Mod 6 counter. So, this will be 3, 2, 1, 0. After 4 clock signals, till 4 clock signals, this will remain low only. Once the count is over, this out goes to high. As long as this gate is equal to high, so this will be remains high only. Once if I make gate is equal to again low, so you have to make a new value, you have to load into the counter. N is equal to 4, you have to load into counter 0 here if I take these signals. Okay. So, where this particular mode 0 will be useful. Okay. So, as the name implies, interrupt on terminal count. Once the count is over, I can interrupt the microprocessor. So, basically this will be used for generate accurate time delays. Under software control. So, because this is under software control, this will produce accurate time delays. Okay. Upon the terminal count, the microprocessor is interrupted. If out is connected to interrupt of 8086, that is why the name interrupt on terminal count. So, I will give some examples so that this operation will be clear. So, example 1, so what value has to be loaded? The value that is to be loaded will be here. So, depends upon this the value that is to be loaded depends upon the time delay that we want. So, we have to load the appropriate count value. Okay. So, this desired delay will be decided by count value. Counter will be loaded with a count which is correspond to desired time delay. However, this time delay will be decided, this depends upon the clock. Okay. Suppose if the clock frequency is 10 megahertz, the highest frequency, and after every 4 clock signals, if you want to interrupt, then the out signal will be having 4 clock signals, means this will be time period will be the time period of this one will be 1 by f 0.1 microsecond. So, if you want to load the count with n is equal to 4, if n is equal to 4, for every 0.4 microseconds this microprocessor will be interrupted. Okay. So, this depends upon the time that is required. If I want some other time, accordingly you have to choose this n value. Okay. So, here I want to load counter 1 with a value of say 6F50H. Okay. So, I want a delay which is correspond to this count value. After the count is terminated, open a relay or valve. This is something like if the in a bottling industry, if I place the bottle here, and if I want to feed this bottle with some liquid which is controlled by some relay here or some valve. This valve can be on or off. This I am going to control by using 8255. This if I connect to the 8255 of the 8086 kit. If I connect to say PC 0. If this is 1, valve will be opened, so liquid will flow into the bottle. If this is 0, valve will be closed, so there will be no liquid into the bottle. So I want to feed this bottle with some level. So this level in bottling industry, if you want to fill the bottles with some medicine, some syrup, okay. So we have some prescribed limit. So the time taken to fill the bottle up to here is, say, let us assume that if I feed the counter with 6F50H, the corresponding time. So within that corresponding time, the bottle will be filled with this. Okay. So for that much amount of time, you have to open the valve, and then again you have to close. Then you have to move this conveyor belt. So you have to allow the next bottle to come this position, and that also has to be filled with the same amount of the time. Okay, like that we are going to fill the bottles in a sequence. This is second bottle. Once this moves in this direction, we will move this here just below the valve. Again we will open the valve for the same time, which is decided by this count, so that this also will fill up to this point, like that. So we will fill these bottles in a industry. Okay. So I want to open a valve once this end of the count is reached. Okay. So what is the program for this one? Before writing the program, what will be the control words? I want to use counter 1 in mode 0, because this is on the terminal count, we have to interrupt. Okay. So I want to use in mode 0. So what is the control register, which you have discussed in the last lecture? This is 0 for binary counting. We want only binary counting only. So this is 0. These 3 bits will decide the mode. So because we are operating in mode 0, these 3 will be 0 0 0. Okay. So these 2 will decide RL1 or RL0, RL1, RL0. So this is 1 1 is total 16 bit count. First it will take the lower order 8 bits, then higher order 8 bits. So here, because our count is 16 bit, so you have to load with 1 1, so that it will first take the lower order 8 bits and then higher order 8 bits of the count. Then we have these 2 signals are select counter. For counter 1, this will be 0 1. 0 0 means counter 0, 0 1 means counter 1, 1 0 means counter 2, 1 1 is illegal here. Okay. So what will be the control word? 70H. And throughout this programs, I will assume the same addresses, which is 00H is counter 0 address, 01H is counter 1, 02H is counter 3, and control register is 03H. So because I am using counter 1 whose address is 01H. First of all, we have to feed this 70H into control register. Move AL comma 70H out 03H comma AL. So this 03H is the address of control register. So with these 2 instructions, so counter 1 will be selected in mode 0 for 16 bit count. Okay. And this is binary counting. Then you have to load this counter with the 16 bit value. First LSB, then MSB into counter 1 whose address is 01H. Similar type of the instructions. Move AL comma The lower order count will be in this 6F50H 50H, where you have to feed this into counter 1 whose address is out 01H comma AL. This will load the counter 1 lower order 8 bits of counter 1 with 50. Then higher order 8 bits you have to load with 6F. So, you take move AL comma 6F, then out 01H comma AL. This will load the higher order eight bits of counter 1 with 6F. So, we have loaded the count. So, then the operation will start. Once if you make this gate is equal to high, so after this read bar goes to high, in the next negative edge onwards the count will start. So, at this point count will end. So, here this will be terminated. So, you have to wait until the count is terminated. So, jump here itself. Once the count is terminated, the microprocessor control will move from here to interrupt service subroutine, because I am going to connect this out signal to the interrupt of 8086. Here what is the program that I have to write? So, I want to open the valve, so which is connected to PC naught. So, what are the instructions? Move AL comma, because I want to program this PC naught as output port. So, we can use 80H to program all the ports as output ports, out FFH. If I assume the same addresses FFH comma AL, this will program all the ports as output ports in mode 0. Then move. So, if this is 1 means valve opens, 0 means valve closes. So, 1 you have to take AL comma PC naught means 0 1. So, that the last LSB bit becomes 1, out port C address is FEH, then I return, interrupt return. So, whenever this terminal count is reached, this will go and open the valve, again it will come back to the main program. Okay. In the main program automatically again you have to load that value, this 6F50. So, this will generate a time which is correspond to filling of this bottle. Okay. So, like that we can use this mode 0 operation to control the industrial process. In mode 0 itself I will take another example. I will take another example in mode 0 itself, where the counter latch, this is example where I will discuss about counter latch. So, we have discussed about this RL1 and RL0 of this control register. There we have explained that 00 is correspond to counter latch. Means what is this counter latching is, while the counter is counting the count, while the counter is in progress, So I want to read what is the count value in between before it reaches to 0. After some time delay, I want to read what are the contents of the counter. So that is also possible. That particular operation is called counter latching. After some delay, the contents of counters can be read. So this particular operation is called counter latching. For that, so initially I will load counter 0 or counter 1 with n value of ff h. Say this is correspond to a delay of say some 10 microseconds, but I want to read the counter status after 2 microseconds. Okay. So further the program will be move AL comma 70H, as you have discussed it. For 70H is for programming the counter 1 in mode 0 and 16-bit count value. Out 03H comma AL, so control register. Then we have to load FFFFH, move AL comma FFH, out 01H, because this is counter 1 01H, whose address is 01H comma AL. Again you have to write, because FF remains same, so no need to load this the other value into AL. I will write another time out 01H comma AL, so that the same AL will be transferred to counter 1 twice. So FF. So the counter 1 will be loaded with FF. So this goes on decrementing the count, because this will be a down counter. After one clock signal, this becomes FFFE. So like that, upon every clock signal at negative edge, this count is going to be decrease. Okay. So in between, I will write a call subroutine, call delay. So this delay I want to write as for 2 microseconds, because I want to read what are the contents of the counter after 2 microseconds. So that is why I am writing this call instruction. Then I have to latch this counter. For latching of the counter, this RL1 and RL0 should be zeros. Okay. For reading the 16-bit count, RL1 and RL0 should be 1 1. Okay. So what are these bits now? So we have out of this 8 bits of the control register, D7, D6, D5, D4, D3, D2, D1, D0. This is binary count, so this remains 0, and this will be 3 bits will be for mode 0 0 0 0, and these 2 bits will be for RL1 comma RL0. So for loading this 16-bit value here, I have taken this D4 and D5 as 1. But now to latch, these two should be zeros, and because this is counter 1, these 2 bits will be 0 1. So now what will be control word? This is 40H. For latching operation, after this many seconds I want to latch. So what is to be loaded into control word register is move AL comma 40H, then out 03H comma AL. Now I have loaded this control register with 40H, which correspond to latching of the counter. Okay. So with these two instruction, counter will be latched. Whatever the contents of this counter at that time whatever the count, it can be say some E540H something after this second. This will be latched onto a register, latched onto the register. So, this register contents we can read into the microprocessor, then we have to jump here itself. You see how we can read the contents of the counter while the counting process is in progress. Okay. This is another application of this mode 0, which is called counter latching. Okay. So, the next mode is mode 1. Is called programmable one shot. So, in mode 1 we have clock correspond to any of the counters. This is same as mode 0. We have to take the clock with some particular frequency which ranges from DC to 10 megahertz, depends upon the application. This is clock signal. Clock, I am not writing clock 0, clock 1 or clock 2. So, it depends upon the counter which we are going to use. Then here also this write bar signal has to be make low to load the count. Say n is equal to same 4. Okay. For explanation purpose I am taking smaller values here. Okay. Otherwise this can be a 16 bit count, varies from 0000H to FFFFH. Okay. Now, a additional point here is, unlike this mode 0 where the gate signal will be always high, here the gate signal will initially low. After this is gate signal is initially low. After this write becomes high, this will go to low to high. So, at the rising edge of this gate, after that whatever this negative edge of the clock, so this is the negative edge of the clock after this is after the negative edge of this. So, this negative edge of this clock onwards, the out was initially high, out signal initially high, then at this point it starts counting. So, this is one count, so 4 becomes 3, after this another clock signal 3 becomes 2, after another clock signal 2 becomes 1, after another clock signal 1 becomes 0. Once 0 is reached, this will go again to the high and it will wait until again the new value of n is loaded. So, out will be initially high, then it will goes to low for this many clock signals 1, 2, 3, 4, then after that again go to high. Okay. Again this will be reloaded with n is equal to 4. So, if I make this gate as low to high transition, again n will be reloaded the same value and again it will goes to low for these 4 clock signals, again it will go to high. This process will repeats. So, why the name programmable one shot is here, this width of the signal is programmable. This is programmable. If n is equal to 4, this is the width. If n is equal to 5, you will get one more clock signal. So like that, this width is programmable. So that is why the name programmable one shot. Okay. Next, coming for the mode 2. Mode 2 is called rate generator. So this basically will be used for dividing the frequencies. This will act as divide by n counter. Here also we will be having clock. This is the clock of a particular counter. This is clock. Here also you have to make write bar is equal to 0 and you have to load with some value, n value. Say n is equal to same 4 only. This is write bar, and here also you have to make gate signal, like mode 0 gate signal will be always high. And out signal will be initially high, so after this write bar goes from 0 to 1, the next immediate negative edge onwards. This is negative edge, this is 1, so this was initially high, then it will goes to the low for n minus 1 clock signals, again it will goes to high for 1 clock signal. This is 3, 2, 1, 0. This is for n minus 1 clock signals. Here n is 4 means 3 clock signals. It will go clock cycles. This will go low. Then for 1 clock cycle it will go high. Now if I compare the frequency of this, the clock, how many clock signals are there in one period of this one? From here to here, this is one period of out. So this is one period of clock. If I call this one as T, 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 this if I call as one period of this one as some T dash. This is T, another T, another T. So what is the relation between T dash and T? T dash is equal to 4 times T. So time period is 4 times means frequency, if I call this F dash as the frequency of out signal, this will be equal to, if F is the frequency of clock signal, F by 4. So the frequency of this out signal is divided by 4, that is by the name divide by n counter. Okay. This is basically used for dividing the frequency by some factor. Okay. So by changing this n value we can obtain any counting value. Okay. If I take an example, suppose if I want to generate binary as well as BCD, I want to implement divide by 16 binary counter. So what is the program for this one? So you have to first operate one of the counters in mode 2. Okay, let us assume that I am using counter 1. I want to operate counter 1 in mode 0, and 16 binary means we have to give this 16 number in hexadecimal form. 16 decimal is equal to 10 hexadecimal. You have to give 10, which is 8 bit only. Okay, so for the 8 bit, and this is binary counting, so the last bit will be 0. Then mode is mode 2 means 0 1 0. These three signals will decide the mode. Then RL1 RL0, this is only the lower order 8 bits only 8 bit operation. So this will be 0 1. Then select counter, I want to use counter 1, which is 0 1. So what is the control word? This is 5, this is 4, 54H. So you have to load 54H onto the control register whose address is 03H. (03H, AL). So these two instructions will load control word register with 54H, so that the counter 1 will be operated in mode 0 and it will act as only 8 bit counter. Okay. Now the count has to be loaded. Count will be 10H because I want to operate as divide by 16 counter. Move AL comma 10H out, because we are going to use this as a counter 1 whose address is 01H comma AL. So these two instructions will load counter 1 with 10H, so that if I connect this out to the CRO, this is just we have to jump here itself. If you connect this out to the CRO, so we can see that the frequency of this out signal will be 1 by 16 times that of the clock frequency. Okay. And I will give second example where I want to use as BCD counter. Implement decade counter. Decade is nothing but mod 10 BCD counter. Using 8254. This is nothing but mod 10 counter BCD counter. Okay. So here we have to give directly a 10 value, not hexadecimal value like here. Here because this is BCD count. Changes here will be, so here this 0 becomes 1 because this is BCD count. This becomes 1, so that I can directly give this 10 into the counter. Then coming for these 3 bits, these 3 are 0 1 0 only because mode is mode 2, and this one is also only 8 bit only. So this will be 0 1, 0 1 because 8 bit, and these two also 0 1 because this is select counter is counter 1. So this control will be 5 5H. Move AL comma 5 5H. 5 4H means binary counting, 5 5H is BCD counting. Out 03H comma AL. So that the 8255 will be operated in decimal mode. Then what is to be loaded? 10. Move AL comma 10H out onto counter 1 whose address is 01H comma AL. So this will divide, if I connect this out signal to CRO here, this will divide by 10, which is decade counter. you have to wait, so that continuously this operation will repeats, jump here itself. So, this is about this mode 2 operation, which is a rate generator. Basically we can divide the frequency by any factor. So, this type of the frequency division will be useful in even microprocessors also. Microprocessor will be operating at higher frequencies, and if I want a peripheral device which can operate in lower frequencies, we can directly take the microprocessor clock and you can pass through the this divide by n counters to generate the lower frequencies. Okay. So, the remaining 3 modes we will discuss in the next class. Thank you.